Part one deals with the titration. What is a titration? A titration is when we try to do a reaction in lab where we get just the right amounts of each reactant. And so let's say we're reacting A and B. You know, there are different ways to get just the right amount. We could weigh it out, or we could measure it out. Weighing out sometimes is difficult because you don't know the purity, and sometimes, let's say B is a little bit impure, and so what you think you're weighing is not actually what you're getting. And so in a titration, what we do is we just continually monitor the experiment and then determine when it's over. So for example, we might be able to do a precipitation titration. In a precipitation titration, you keep adding, and then you're just going to get more and more precipitate, and eventually you're going to stop getting more precipitate. When you stop getting more precipitate, that's the end of the reaction. And that would be what we consider a stoichiometric amount. And so a lot of reactions we do is excess reagent, limiting reagent. In a titration, we don't want excess reagent. We don't want limiting reagent. We just want the correct amount of all the reagents. For precipitation, it's easy to see sometimes. Well, sometimes it's difficult to see because it just gets cloudy. You don't know if you're getting more precipitate or not. But maybe something like bubble formation, effervescence. With effervescence, you should be able to see when the bubbles stop forming, that's when you should stop the reaction. Or you might have a balloon, you know. When the balloon stops growing, that's the end of the reaction. You know, as the gas fills up the balloon, you're not getting more gas, so you better stop because there's nothing more to react. All right, so titration is a very specific technique where we try to get stoichiometric quantities of both reactants. And so we're going to get proficient at one of the techniques of titration. Two, to gain familiarity with the concept of stoichiometry. Yeah, stoichiometry, excess reagent, limiting reagent, stoichiometric quantities. What we want here are stoichiometric quantities. Three, to determine the molarity of a basic solution. Molarity is just the concentration, the composition. So for example, we're going to be doing a titration of an unknown base. The base is not unknown. We know what the base is. The base is sodium hydroxide. What's unknown is the composition because this is sodium hydroxide aqueous. Sodium hydroxide aqueous contains sodium hydroxide and water. Well, how much sodium hydroxide and how much water? We want to know the composition. One of the easiest ways of expressing the composition is by percent by mass. You know, how many grams of sodium hydroxide, how many grams of water, or how many grams total would be percent by mass. There are other ways of expressing the composition, and probably the most common one is molarity for solutions. Molarity is defined as the moles of component A, in this case HCl, over the liters of solution. So if I have 1 liter of that liquid solution, it turns out I have about 0.1096 moles. 0.1096, that's fairly precise. That's 4 sig figs. And not only that, that's pretty accurate. Somebody's tested the accuracy of that. And so if we know the composition of something with good precision and good accuracy, then we call it a standard. Have you heard of the National Institute of Standards, NIST? You know, they have a budget in the billions or maybe even $100 billion budget. And that's all they do. They just do standards. So for example, they have a peanut butter standard there, and that peanut butter, it's just a jar of peanut butter, but it costs like $30,000 because everything in there has been accurately and precisely determined, you know, all the components. And so that's why it's so expensive. It's so expensive because they've analyzed it and standardized it. And what do the people use that for? Well, people use that for comparison, or for testing methods or that. They have gold standards, this standard, that standard. So, so we're going to use this. This is just a standard that was produced in the lab here. And so we know what the composition of this acid is. It's hydrochloric acid here. And this hydrochloric acid standard, I mean, this looks like water, but it's just HCl dissolved in water. We're going to get from the stockroom. And so the hydrochloric acid, you're going to bring a 250 milliliter beaker there, and they'll just exchange it for one that contains hydrochloric acid. And then for the sodium hydroxide, we have that in a different container because we don't want to get them mixed up. And so the sodium hydroxide is in this flask. Do you recall what this flask is named? Florence flask. How about this flask? Erlenmeyer flask, Florence flask. Okay, we're going to use both today. And so bring your 250 milliliter Florence flask, and then they're going to put sodium hydroxide in here. Sodium hydroxide is a good strong base. So we know that the base is sodium hydroxide. What we don't know is how much sodium hydroxide is in here. You know, and what we want to do is we want to figure out how many moles of sodium hydroxide are in here per liter. I don't have a full liter. We don't need a full liter. We just get the ratio. We get the moles per liter ratio. Okay, but I do know how much mass I have. So the reaction I'm going to be doing here is HCl plus sodium hydroxide. What are the products of this? Sodium chloride and water. And so the way we're going to accomplish this reaction is I'm going to put some hydrochloric acid in here. And then I'm going to start reacting the hydrochloric acid in my Erlenmeyer flask with sodium hydroxide. When do I know when to stop? How do I know when to stop? So I pour in some hydrochloric acid here, and then I have some unknown sodium hydroxide over here. And I'm going to add just the right amount of sodium hydroxide. What is just the right amount? And so what I have to do is I have to figure out how much sodium hydroxide do I need. And in this case, I'm not going to calculate it. I'm going to look for something. Should I look for the formation of water? You know, once I stop forming water, then the reaction's over. Well, can you even tell if you're forming water or not? No, there's already so much water in here. There's no way we can tell. How about salt? You know? Can you see salt being made? Sodium chloride? What? Is that a precipitate? If this were a precipitate, maybe we could see it being made, but is it a precipitate? No. It's an aqueous solution. And so do you know what it's going to look like? It's going to look like CCS plus CCS. What was the CCS again? Clear colorless solution. CCS plus CCS yields CCS. So can we even tell anything happened? No, we can't. Maybe what you could do is taste it, but do you know what drain cleaner tastes like? Probably not, right? But you know what salt tastes like. You might know what hydrochloric acid tastes like. It's pretty sour. I've heard this is pretty bitter, but I don't want to put any. So we're not going to do, I don't know what we're going to do. And so based on visual observations, we can't tell when we've added just the right amount of sodium hydroxide. But anyway, for experiment 6, 7, what was it? The experiments we did last week? 6, 7. Well, anyway, for that experiment, you're not going to turn in the report sheet. I don't want the report sheet for that. What I want are the CE, IE, and NIE for each reaction. If you already had those checked off, then you don't have to turn them in. But I wanted those with the observations. You know, the observations would be like heat. You know, maybe you might be able to feel the heat, but probably not. I mean, not much heat is generated. Not enough that, because the concentrations are fairly low. I mean, that's not even 1 mole per liter. It's 1/10 of a mole per liter. So the concentrations are fairly low, so we're not going to generate that much heat. And water is such a good heat sink, you might not feel it at all. But for the for last week's lab, what I want the equations for the reactions and some observations. Just simple observations. CCS plus CCS yields CCS, that kind of thing. And so how are we going to figure out when we've added just the right amount of sodium hydroxide? There's nothing that tells us this. And the just around right amount of sodium hydroxide we call an equivalent. We need to add one equivalent of base that is, equal to the stoichiometric amount. The equivalents are a little bit more complicated than that, but I'm not going to get into it. And we do have one way to tell. The one way we're going to tell is this. We have a dye or an indicator called phenolphthalein. You guys might have used this last week, phenolphthalein. And phenolphthalein has two colors. In acid, it's colorless. In base, do you know what color it turns? Pink. Right. And so we can tell this. What we're going to do is we're going to start off with the acid in our flask. We're going to start off with the acid and the indicator or dye in our flask, and then add the sodium hydroxide. And as the sodium hydroxide reacts with the HCl, the concentration of HCl goes down. Eventually, the concentration of HCl will go down to 0. When you have no more HCl left, then that's where we want to stop. But we don't know exactly where that is. So what we're going to do is we're going to add just a little bit more sodium hydroxide. So once we consume this all the way to 0, a little bit of extra sodium hydroxide is going to turn this color to pink. So does that make sense here? And so even though, yeah, we want stoichiometric amounts, we're going to go with a slight excess of sodium hydroxide. That slight excess is going to be a minimal error. In fact, what I want to do is I just want to go with a half a drop extra sodium hydroxide. How can I get half a drop extra sodium hydroxide? I have to be very careful. The way I get a half a drop extra of sodium hydroxide is I go from colored HCl, no, that's not colored, colorless HCl to colored, just slight excess of sodium hydroxide in a half a drop. And so let me talk about how we do titrations next. But usually in lab, what we do is we read the experiment before coming to lab. I didn't have you guys do this, so we could just read through this together. It's pretty short. If we go to the discussion, a standard solution is a solution whose concentration is accurately and precisely known, usually to 4 or more sig figs. That's the precision there. 4 sig figs precision. 4 sig figs precision is pretty good. A titration is a precise analytical technique for determining the concentration of a solution. It's not just for concentrations, concentration of the composition of the solutions. We can do other things with titrations as well. The procedure involves adding a standard solution to a solution of unknown concentration until equivalent amounts of each solution have been combined. Equivalent amounts means stoichiometrically equivalent amounts. Stoichiometrically equivalent amounts might not be the same in terms of volume. And so just keep that in mind. In other words, titration is a method for determining the amount of a standard solution required to completely react with a given amount of solution of unknown composition. Unknown concentration. I shouldn't say composition because we know what the composition is. It's just sodium hydroxide and water. In an acid-base titration, we wish to determine the point at which just enough base is added to completely neutralize a given amount of acid. So this is the stoichiometric endpoint. This is when we have stoichiometric quantities of each. And so we have 3 ways of doing a reaction. We could have limiting A, excess B. We could have excess A, limiting B, or we have stoichiometric, just the right amount of A and B. Well, that's what we're shooting for here, stoichiometric. This corresponds to what we call the equivalence point. But we can't see the equivalence point, so we need some kind of way to detect it. And the way we detect it is by adding a little bit extra sodium hydroxide. So little, error is negligible. And so this titration has an endpoint. The endpoint is where we get some kind of signal. In the case of us, the signal is going to be going from colorless to pink. And that would signify the endpoint, which is very close to the equivalence point, the stoichiometric equivalence point. This titration endpoint is made observable by use of an indicator. An acid-base indicator is a substance which changes color as acid or base concentration changes. For this experiment, a convenient indicator is phenolphthalein. It is colorless in acid, pink in base. So we're going to use these. These are common in titrations. These are called burettes. And so pieces of glassware called burettes are used to precisely measure. And these are calibrated too, so they're pretty accurate. To accurately and precisely measure and control the volume of each solution. When a basic solution is added to a sample of acidic solution containing a drop of phenolphthalein, the neutralization point is reached when the solution contains only water and a salt. At this point, the solution is still colorless. Addition of another drop or fraction of a drop, we want to go with a fraction of a drop, like a half a drop, of the basic solution changes the color of the solution to pink. This is the titration endpoint. And so in other words, we're going to have our acid, and then we're going to start adding base until we get right to the equivalence point, and then add a half a drop more to get to the end point being the pink color. By experimentally determining the volume of sodium hydroxide solution required to neutralize a given volume of HCl solution, the molarity, which is the composition in terms of the concentrations, is or can be calculated. Okay, that's part one. So let's talk about cleaning the burettes. So for this one, we need goggles because sodium hydroxide you can buy in the supermarket, and sodium hydroxide is used for what? Drain cleaner. And so have you? I don't know if you've ever gotten sodium hydroxide in your eyes, or drain cleaner. Have you gotten drain cleaner in your eyes? Extremely painful. Well, you can tell if you get sodium hydroxide on your fingers. If I spill a little bit of sodium hydroxide on my fingers, they get very slippery. Have you ever felt that? Basically, they break up the cell membranes, apparently, and that's why it's so slippery, because your cells are being broken apart. But if your fingers feel slippery, don't rub your eyes, because that's how people get sodium hydroxide in their eyes. That's one way. The other way is it splashes into their eyes. And so we have two burettes here. We're doing Chem 4 style titration. Chem 4 style titration is for beginners. Chem 1A style titration is for more advanced students. And so in Chem 1A, we just use one burette. In Chem 4, we're going to use two burettes. In Chem 1A, typically we just use the one base burette, and that's it. And so the setup is a little bit longer for Chem 4 because we need two burettes. The other problem with the Chem 4 titration is that using two burettes is a bit more risky, because do you know how much these burettes cost? How much? 500? Maybe now they cost 500. In 2019, these cost 187. So that was 2019. That was what, 5 years ago? So maybe now they're more like 400 now. Maybe not quite 500. Well, a lot of students have broken these, unfortunately, and it's still a lot, $200 back then. I don't know the current price of these. Well, one thing we don't know is, we don't know if the last person that used this cleaned them out. There could be residual sodium hydroxide. So even if you're washing the dishes, you can't assume it was clean, or you can't assume that residue can't hurt you. There could be sodium hydroxide residue here, and we don't want to get that splashed in our eyes. And so what I have here is a big waste beaker. I don't want to walk back and forth to the waste bucket over there, the gray ones or the red ones. And so I'm just going to dump all my waste at my lab station. So the first thing you're going to do is assume that the last person that used this didn't clean it out. And hopefully they used blue for base, and then we're going to use this orange or red for acid. And so the first thing I'm going to do is I'm going to put some water in here and then rinse off the inside walls of any residue there. And then this is called a stopcock or a valve. When it's perpendicular to the line, it's closed. I'm going to make this parallel to the line, open it, and then let it drain and rinse the tip of the burette. It drains kind of slow, so I might dump out the rest out the top here. Okay, rinse it a couple of times with, do we have distilled water here? Actually, we don't have distilled water here. We do have, distilled water will have a label saying DW. DW stands for distilled water. Ours says DI. Do you know what DI stands for? Deionized water. Distilled water is a lot more expensive because in order to make the distilled water, you have to boil the water. I'm not sure if it's still that much more expensive because the resins that we use for deionization have skyrocketed in price too. That's why we have to conserve our deionized water. But since energy costs have gone up, I think electricity has tripled and gas is, more than doubled. It's expensive to make distilled water. All right. How can I dry this though? There's still some water in here. Is there a way to dry this? Not easily. I mean, you could try jamming paper towels in here, but forget that they're going to get stuck in there. It'll be a nightmare. And in fact, if it's still dirty, I might wash it with soap and water. We have special brushes that have really long stems, and there's just cylindrical brushes that fit into the burette. You can really wash or scrub the inside of these, but we're not going to bother with soap and water. We're just going to use DI water to give it a rinse. But the problem is I have DI water residue in here, and if I pour in my solutions, then that will change the composition. That is, I'll have more water in there, and in other words, I'll change the concentration. And so what I need to do is I need to rinse out the water out of here. There are different methods that people use to rinse out the water. The method we're going to use is I'm going to sacrifice some of my sodium hydroxide to use as a rinse. And so here's my sodium hydroxide unknown solution. And I'm going to use a little funnel for this because pouring out of a Florence isn't so easy. And the funnel, what I'm going to do is I'm going to make a little air gap here so it drains quickly. Otherwise, the funnel volume is extremely small. This is a tiny funnel. And so it's easy to overfill this. And so I'll pour in maybe about 10 mils or something, or less. That's probably too much. And then what I'm going to do is I'm going to just try to rinse the water off the walls of this. I have this much, and you can hold this almost horizontally without it spilling out. Weird. And then just rinse off the inside walls here, and then I'm going to rinse off the valve and the tip of the burette. And then maybe drain off the excess up the top here. Maybe rinse it twice, that should be enough. Okay, once I've thoroughly rinsed this with DI and the acid or the base solution, in this case it's blue, so I'm using the base solution, I'm going to fill it. Alright, so I make a little air gap here, and I'm just going to fill this up. I'm going to fill this up above the top mark here. And so I filled it above the top mark here. The reason I did that is because I need to get rid of the water or whatever is in here, purge that out. Not only that, what can happen is there can be air bubbles in here. Do you see the air bubble there? There's an air bubble in there. We need to get rid of that. Sometimes these air bubbles are stubborn. Sometimes they come out. That one just came out. But what we're going to do is we're going to see if there's an air bubble trapped in the valve. And so normally what I do is this. Even though this is full, I can tilt this almost horizontal like this. And it's much easier to push the air bubbles out horizontally than vertically. This is like if you put a ball in a swimming pool and try to push it down. This is what we're trying to do. We're trying to push a ball down the swimming pool or deeper into the water. But if I tilt this horizontally, this is just like trying to push a ball horizontally underwater, which is going to be a lot easier. And so I'm going to just shake this a little bit, make sure there are no air bubbles left. Okay, and that looks good. All right, now I'm below the 0 mark. These burettes are marked with 0 at the top, 50 at the bottom, and this is in milliliters here. But you know what? I'm not going to refill it. You know, I don't want to waste time getting the start right at 0. We're going to start a little bit below 0 here. In fact, let's see. You guys recall how to read a burette. Let's say this is the 0 mark on the burette, and then each line is 0.1 milliliters. So this is 0.0, 0.1, 0.2, 0.3, 0.4, and then 0.5. A little bit longer line, 0.6, 7, 8, until we get to 1 milliliter. So I'm slightly below 0 here. And then what I want to do is I want to read at the bottom of the meniscus. Water forms a concave surface here. And so we need to measure it right at the base, right at the bottom of that valley. And so we get our eye level with that, and then what would you read this? Well, I would read this as it's between 0.1 and 0.2. And so would you call it 0.1 milliliters? No. Would you call it 0.2? No, it doesn't match any of those lines. In fact, it looks like it's closer to 0.2, so what would you call that volume? Would you call it 0.15, like halfway between the 0.1 and 0.2? Like this is between 10 and 20, excuse me. And so would you call it 15, halfway between 0.15? No. It looks like it's closer to 0.2, so I'd call this like 0.17, 0.18. Would you agree? All right, so when we do these burettes are expensive because they have higher precision. The precision that these burettes read to is to the nearest hundredth of a milliliter. So we need 2 decimal places after the decimal point. In other words, we need 2 places after the decimal point is what I meant. Okay, that's going to be our initial. Now, my burette's leaking. Do you see my burette's leaking? There's a half a drop hanging there. Do you see that? It's not a full drop yet, but pretty soon it's going to grow to a full drop. Once it becomes a full drop, you know what's going to happen? It's going to fall down. And that's because my rubber O-ring is trashed. I only have half the rubber O-ring here. And so what I'm going to do is, if yours is leaking, one thing you can try to do is you can try to tighten the valve here. So for example, if the valve is too loose, this is what's going to happen. If the valve is too loose, it's leaking everywhere here. And so what I need to do is I need to tighten this valve. Let me try to tighten this. But the O-ring now the O-ring's set. So it looks all right. But you don't want it too tight. If you get this too tight, it's hard to twist. We need to be able to twist this easily. All right, now that's screwed up my initial. My initial should be between 0 and... To ensure that I have enough base in here, I need my initial value to be between 0 and 15 milliliters. Actually, this is getting close to 15. I'll probably pour a little bit more base in here. I don't want to run out. And I'm not going to waste the time getting it right on 0, so I'll just fill it up. And now looks like I'm between 1 and 2 milliliters. The meniscus lies right on 1.2. If the meniscus lies right on 1.2, what do I write down? Do I write down 1.2 milliliters? No. Do you know what I write down? 1.20. You know, if it's right on the line, add a 0 to the end. That's what we do. All right, so now this burette's prepped. So I do the same thing for the acid burette. I rinse with DI water, and then I rinse out the water. I'm going to rinse out the water using or sacrificing some of my standard acid solution. The standard acid solution is in the beaker, so I probably could get by without the funnel because the beaker has a little spout here. But I'll go ahead and use the funnel here. And so I'll make a little air gap in the funnel. Fill this to above the 0 mark. And then purge the air out of the tip. There's a big bubble in here. Sometimes you could do it vertically. I do it vertically. This bubble's not coming out. Oh, maybe there it goes. Sometimes you could shake it and the bubble will go up. Or sometimes, if it's really stubborn, just hold it horizontally. This bubble is really stubborn, so I'm going to hold it horizontally and then shake it back and forth. Okay, there it went. 3 bubbles just left. There. And now I'm between 3 and 4 milliliters. It looks like I'm at 3.18 milliliters as my initial. So we need to record the initial volumes. Actually, there are only 4 volumes that we need to record. The 2 initial volumes, the acid and the base, and the 2 final volumes, the acid and the base. That's it. But we aren't going to record the final volumes until we're absolutely done with everything. And so I'm starting at about 3.1, 3.2 milliliters, but I need to know to 2 decimal places. So this is 3.18 milliliters. Yours is going to be different. And then what we're going to do is we're going to pour about 20 milliliters in there. So I'll stop around 13. So that's about 13. I went a little over 13. But I'm not going to record this volume because this is not my final volume yet. The final volume readings are going to be at the very end of the experiment. And so I have my acid in here. And to make this visible to the naked eye, I need to add my phenolphthalein indicator here. So I'm just going to add 1 drop. 1 drop is enough, or you could add 2 drops. But whatever you do, if you do 1 drop or 2 drops, make sure you always do the same. I'm just going to do 1 drop, or maybe I'll do 2 drops. It says to do 2 drops, so we'll do 2 drops. Don't overdo it with the indicator. The indicator itself is also an acid. And so that could change the stoichiometry a little bit of this. Okay, the great thing about using Erlenmeyer flasks are it's easy to mix liquids in an Erlenmeyer. If I mix liquids in a beaker, by swirling it like this, it's easy to splash out. But with an Erlenmeyer, you can mix it vigorously by swirling like this and it doesn't splash out. That's because of the concave walls. Not concave, but what do you call that? Tapered walls. All right, so now I have phenolphthalein and acid. Phenolphthalein and acid is colorless. Now, I don't know how much base I need to add. I just need to add the right amount of base. And so I'm right-handed. I'm going to twist this. And so the first titration is going to be quick. I'm just going to let it drain. Oh, I didn't get all the air bubbles out. Shoot, there was 1 little air bubble that came out. That 1 little air bubble screws things up. I probably should start over, but I'm not. Okay, do you see the pink color here? No, I need to go from colorless to pink color within a half a drop. But do you see that pink color? Did you see it disappear? It wasn't well mixed. And so I'm not going to mix it. I'm not going to mix it. I'm just going to let it drain until I get a good pink color and see. Okay, stop here, and then let's see if this one disappears too. Oh, this one didn't disappear. So was that within a half a drop? No, that wasn't within a half a drop. In fact, I was way off. So what I'm going to do, in Chem 1A, what you have to do is if you overshoot it, you dump it in the waste and you start over again, which is a pain. In Chem 4, what we're going to do is we're going to undo this. And so I overshot it, not a big deal. What I'm going to do is I'm going to add a little bit more acid. Let's see. I added about 4 drops of acid. No, I really overshot it. I'll add, that was about 6 drops of acid. No, no, that means I added way too much. So I'm just going to dump it in here until I go back to colorless. It's still kind of pink, you're right. The pink color has to persist for 30 seconds. Is it still kind of pink? Yeah. You have to watch out because we have LED lighting. Still pink. Okay. I'm going to add just 1 drop. Oh, I tried to add 1 drop and about 5 drops fell in. How about now? It's pretty colorless. Okay, now what I'm going to do is I'm going to just add 1 drop. Hopefully I can get this 1 drop to go. Okay, I got 1 drop. Did it turn pink? No. All right, I'm going to go with another drop here. How about now? Do you see any pink? Maybe not. Okay, I'm going to go with 1 drop here. Now, do you see it? Yeah, but that was pink within 1 drop, and I have a 1/4 drop hanging there. That 1/4 drop's already been measured out of here. So what I'm going to do with the 1/4 drop is I'm just going to wash it in with water. So this is 1 1/4 drop. With 1 1/4 drop, I don't want that. I want it within 1/2 drop. And the color's got to persist for 30 seconds. So let's just see if the color persists for 30 seconds. Well, that one has a second's hand. If the color disappears before 30 seconds are up, then we are not there yet. All right, let's say it's been 30 seconds. Do you see the color persist? But that was with 1 1/4 drop. So what I'm going to do is I'm going to add 1 drop of acid to undo it. Okay, so I put in 1 drop of acid. It's still, do you see still a little bit of pink color? What I'm going to do is I'm going to add 1 more drop of acid. So when I do this, I just slowly let that drop build up. It gets bigger and bigger until it's big enough and it falls. And so that was another drop of acid. And now, do you see much color? I see the purple from the LED, but do you see much color here? No. All right, now I'm going to get this within 1/2 drop. My burette's still leaking. Do you see 1/2 drop is hanging there? This, I need to get a new O-ring for this. What I'm going to do is I'm going to just wash that 1/2 drop in here. Oops. I hit it out. Okay, now do you see the pink color again? It came back, but it's got to persist for 30 seconds. So let's see if it persists for 30 seconds. There is a pink color. I rinse off the inside walls of this. So now I have it within 1/2 drop. So I got pink color within 1/2 drop. Will it last for 30 seconds? Well, it's still pink, slightly. Okay, let's say it's been 30 seconds. So I have a pink color that lasted for 30 seconds. I'm done. Now I'm going to measure the final volume of acid and the final volume of base. And then that's it. All right, what am I going to do with that? Well, once I get the initial and the final volume, then I'm going to calculate the total volume of acid and the total volume of base. That is final minus initial, final minus initial. And then what I'm going to do is I'm going to take a ratio. I'm going to take a ratio of the volume of base over the volume of acid, or vice versa, it doesn't matter. And I'm going to get the numbers. And so the ratio should be the same for each titration. Yeah, this is still persisting. The color is still pink. Do you see that? And so we're good there. So what I'm going to do is I'm going to refill these if I need to. It doesn't look like I need to. Maybe I just didn't add enough base. But if I need to, I'll refill these. So I don't want to go below 50 here. And then do it again. So trial 1, let's say I got a ratio of 0.9953. And then I do trial 2. Trial 2 should give me the exact same ratio of base to acid or acid to base. And it wasn't. It was kind of close, 0.9861. And then I do trial 3. And trial 3 was a little different also, 1.0253. Now what I'm going to do here is I'm going to see what the difference is. I want to see what the difference is between the biggest and the smallest. So I'll pick the biggest, 1.0253, and the smallest, 0.9861. And then I'm going to take the biggest ratio minus the smallest ratio divided by the smallest ratio times 100%. And this should be less than 0.5%. So we don't want more than 0.5% difference between these. Ideally, there should be 0% difference between each trial. If there's more than 0.5% difference between your biggest and smallest ratio, then do trial 4. And so we need a minimum of 3 trials with 0.5% agreement, or 4 trials. You can't do too many titrations because we don't want to run out of sodium hydroxide, because we have to use sodium hydroxide for both part 1 and part 2. So you have to conserve your sodium hydroxide. Let's say I finished. Normally, if I finish, then I dump all the chemicals. But in this case, don't dump your sodium hydroxide. If you still have some leftover sodium hydroxide here, save it, because we don't want to run out for part 2. Technically, you should be able to go get some at the stock room, but they won't be so happy. If everybody goes and gets sodium hydroxide, they're going to run out at the stock room. But anyway, that's it for the titration. Any questions? Uh-huh.
For the volume of the sodium hydroxide over the hydrochloric acid, is it based on the final reading?
No, it's based on the actual volume. The volume here of sodium hydroxide is V final minus V initial for the base. So first you have to calculate. Let's say you started at 1 milliliter and ended at 21 milliliters. How many milliliters of sodium hydroxide did you just dispense? 20 milliliters. And so we're going to get the volume of sodium hydroxide used and the volume of HCl used. Not the initial volume, not the final volume, but the delta V. You'll have to calculate that. Okay, any other questions? This is going to be an individual lab, so everybody's going to get practice doing titration. So you're going to go over to the stockroom, bring your Florence flask and beaker, 250 milliliter, and they'll give you the equipment.